Hi, welcome to lesson 23C, Expectation. The goal of today's lesson is to learn what expectation is and how it is calculated. So expectation is just a way of calculating what the expected value is, or what you would expect to calculate or expect to find if running some sort of experiment many times when the outcomes have specific probabilities attached to them. So suppose we've got some sort of random variable x, and the set of x has outcomes x sub 1, x sub 2, all the way up to x sub n. Then each of those will have some sort of a probability attached to them. And so there would be probability 1, probability 2, all the way up to probability n. And this is probability of x equals x sub I. Of course, the I is just an index to say the values of I are 1, 2, 3, etc., all the way up to n. So it just gives us a bit of a format of how to sort through each of these outcomes and their expected probabilities. So then the expected value is basically when we multiply each of these outcomes with their probabilities and then add them all together. So the expected value of such a thing would be x sub 1, the probability of x being equal to x1, plus x2 multiplied the probability of x equals x sub 2, etc. all the way up to x sub n multiplied by the probability of x equals x sub n. So that can just be all shortened down to the sum of I equals 1 to n. Those are all the different places, the term numbers. And then we've got x sub I multiplied by the probability of x equals x sub I, and then shortened even further to the sum of I equals 1 to n, x sub I, the probability of x sub I. Okay, so this is lowercase, this is uppercase. And you just add them all together, and that gives you the expected value, the expected outcome. So that's over many trials. It's an average overall. And that would be how you would get the expected value. So suppose we have n trials of some experiment, and the outcome has some sort of probability p. Then the expected outcome is just np. Okay, so we just have to multiply the number of trials by the probability, and that will be the expected outcome. A lot of times expectation gets associated with games, so like games of chance, etc., which are perhaps illegal in our school system, but it's a good example. Sorry, tough word to reach. It's a good example to use to show this expectation, an example of it. So a fair game, if we want to see if a game is fair, so let's say for example you've got I don't know, some kind of a spinner, just to keep things very simple. We got kind of some sort of a spinner, and we've got the arrow, and you spin that around, and suppose these things are broken up into maybe equal size pieces. They don't even have to be equal size sectors at all, but suppose we do that sort of thing. We're playing a game, and let's say it costs you $1 to play, and then depending on where the spinner lands, you could earn in quotations $0 if it lands there. Maybe just to keep things interesting, earn $0 there, $1 if it lands there, $2 if it lands there, say $10 if it lands there, and actually let's say that's another 0. Why not? Just to keep things interesting. So the probability of each of these, of the spinner landing on each of these, if there are 6 sectors, then the probability, let's say they're all equal size, the probability of it landing on here is 1 over 6. The probability of the spinner landing here is 1 over 6. 1 over 6 here, etc. So all the way around. So then, if you wanted to see if it's a fair game, basically you would take all these expected earnings or winnings multiplied by the probabilities, and you subtract off the cost of the game itself to play, and then see if it equals 0. So fair game is when it equals 0. And if it does equal 0, it's a fair game, then you can play it without feeling you're being cheated. So suppose just for example we say the expected outcome is going to be 0 multiplied by 1 over 6 plus 0 multiplied by 1 over 6, then plus 1 multiplied by 1 over 6, then 10 multiplied by 1 over 6. So if it lands there, you're kind of lucky. Then we'll continue adding down here. We've got 0 multiplied by 1 over 6, and then 2 multiplied by 1 over 6. And then of course you have to subtract off the dollar it costs to play the game, and then we add all this stuff together. So we get 0 plus 1 over 6 plus 10 over 6 plus 0 plus 2 over 6 minus 1. And we'll see what that equals. So 1 6 plus 2 6 is 3 6 plus 10 6, there's 13 6 minus 1, which I'm going to change to 6 over 6. So that gives us 7 over 6, which means that on average you should win, or on average you will win 7/6 of a dollar. You could divide that to get actually the dollars and cents of it, but that means that if somebody were to propose this game to you and say, okay, you give me $1 and we'll spin this, and I'll give you certain values if it lands on certain sectors, and you knew this, and you knew that on average your outcome would be 7 over 6, which as I calculate it is going to be 1.167, so I guess it'd be about $1.17 on average, $1.17 per game that you play. So then you say, heck, if it's only going to cost me $1 and on average I'm going to win $1.17, of course I'm going to play this. So then if for example you played 100 games of this, you're going to shell out $100 to play, of course, but you're going to be winning $117. So over 100 games, you're going to come away with $17. Okay, so that would be it's not necessarily a fair game. You would say it's fair, I guess, for the player, and not so fair, I guess, for the house, I guess if you want to call it. But it's not a fair game because it doesn't equal 0. However, it would be a game that you would want to play. Okay, so fair game is if e sub x equals 0. Okay, and that's basically it for expectation. We're going to go through a few examples tomorrow as usual, and then we'll let you continue working on the practice questions later on. So after you finish this video, please look at examples 5 on page 614, and then examples 6 and 7 on page 615, and then after that take a quick look at exercises 1 through 8, 10 and 14 from pages 616 to 617, and then we'll take a look at all this tomorrow in class. So thanks for watching, and we'll see you in class.